This time, we are going to solve for the kernel and the nullity of a linear transformation involving matrices. Here we have 2 by 2 matrices. The first matrix A has entries 1, 2, 3, 4. In the second, we have 1, 2, -2, and -4. Now, the kernel of this linear transformation, again, is a set of vectors which could come up with the zero vector here. But since this is a matrix, we need to come up with this situation here. Let's say the transformation of vector v is equal to a times certain vector v. And this would be equal to 0 vector of the same space because we are in R2. So we are going to have the 0 vector being 0 and 0. And this v here is the set of vectors that we are going to solve. Let us say that vector v has components v sub 1 and v sub 2 for this given illustration. So let's start with the kernel first. The kernel is a set of all vectors that will satisfy this notation. The nullity, on the other hand, which will be discussed right after the kernel, is the dimension of the kernel of T. Okay, it means it identifies the number of elements are there in the kernel of T. So let's start. Of course, you could multiply your matrix A with your vector V, but the suggestion here is from this matrix here, let's come up with its reduced row echelon form, okay, or just even the row echelon form. Okay, so we'll have here 1, 2, 3, and 4. To make this 0, we're going to multiply -3 to R1 plus R2 for a new row 2. We have here 1, 2. This becomes 0, right? Because you will have -3 times 1 plus this. Then you will have to come up with the next 2 times -3 is -6 plus 4. I have here -2. Okay. With this, we can now come up with the product of -1/2 to your row 2 to have a new row 2. This is now your new matrix. 1, 2, 0, and +1. Now, instead of using the original matrix A for in this form, we are be using this and multiply this with our vector v sub 1 and v sub 2. It's now even easier because we have a simpler form of a matrix. And again, this would be equal to 0, 0, which is your 0 vector here. So once you multiply that, you will have v sub 1 plus 2 v sub 2 being 0, and v sub 2 already equal to 0. So already have the component for your v sub 2. Substituting that here, you will have v sub 1 plus 2 times 0 equal to 0. So v sub 1 is also 0. So these are now the components for your vector v that will satisfy this idea here, making the entire form linear transformation equal to the 0 vector. In short, your kernel, okay, let me have it here. The kernel of T is equal to the set containing the vector 0 and 0. Okay, now let's talk about nullity of T. The nullity of T talks about the dimension of the kernel of T. The dimension of kernel of T talks about the number of vectors that can be found inside our what do you call this one? Our kernel. It can be expressed in this form: the dimension of your kernel. So you might say there's one because there's one vector here, but here's the catch. If your kernel of T contains only 0 vectors such as this, the nullity is 0. Okay? The vector, the 0 vector will not be counted as 1 as a dimension of the kernel because it's just the 0 vector itself. So for this case, since the kernel of T contains 0 vector in R2, the nullity is just 0. Okay? Let's proceed to the second example here and do the same thing. Again, before we use this here, let's come up with the row echelon form of this. You have 1 and 2, negative 2, negative 4. To make this 0, multiply 2 to R1 plus R2 for a new R2. This would mean 1, 2 here. 2 times 1 is 2 times negative, plus negative 2 rather is 0. 2 times 2 is 4 plus this, that's 4. For this, you only have one equation, and if we're going to multiply this with your v vector here, v sub 1 and v sub 2, you will have this equation. V sub 1 plus twice v sub 2 is equal to, of course this is equal to 0. Since there are two variables here, you can let, okay, v sub 2 be an arbitrary constant t. In that case, v sub 1 plus 2v sub 2 be 0. It will become v sub 1 plus 2t equals 0. V sub 1 is equal to negative 2t. Okay? For this, we have these two entries now. In short, our kernel of t is equal to the set containing, we have the first negative 2t and t, okay, such that, or you could do it like this, okay. Let's start with this first. You will have your vector v here is negative 2t and t. Now once you take out t, you will have negative 2 and 1, positive 1, such that t is an element of R. That's your kernel of t. The nullity of t talks about the number of vectors that can be found here. Of course, there are infinitely many because your t can take any values, but just for the specific kernel here, the nullity of t is 1 because there's only one vector here, that's negative 2 and 1. So again, earlier, since the kernel contains 0 vectors, the nullity is 0. Here we have this set for the kernel of t, and there's only one specific, what do you call this one? Aside from when multiplied to a certain t, you only have one here. So nullity of t is just 1. This is how we solve the kernel and nullity of a linear transformation using matrices. Thank you very much for watching.